The darkness between the stars is the true nature of the cosmos. Astronomer Carl Sagan once noted that the universe is mostly empty, and that statement holds a profound and unsettling truth. We are about to explore the great intergalactic void, the vast deserts of nothingness that make up most of space. By the end of this journey, you will understand why this emptiness is the single most important feature of our universe, dictating its fate and our place within it. How did these colossal voids form, and what hidden forces are actively stretching them wider? We will see how the great nothing holds the keys to dark energy, the Big Bang, and the very structure of reality. What does it mean for us that we live in a universe dominated by empty space? Think of the universe as a sponge, a vast cosmic structure where the bright galaxies we see are just the thin, shimmering walls of soap film. The overwhelming volume, the deep dark bubbles inside, are the voids. This is the great intergalactic void, and to call it empty is to misunderstand its nature entirely. It is not a simple absence of light. It is a specific, measurable region of space where the density of matter can be up to 100 times lower than the average across the cosmos. These are not small pockets, they are staggering deserts of near nothingness, each one spanning hundreds of millions of light years from wall to distant wall. Cosmologists like J. Richard Gott described the large-scale structure of everything as a cosmic web, a magnificent lattice of glowing filaments and dense clusters where galaxies gather. But the voids are the true architecture, the dominant volume of the universe. They are the empty rooms that define the shape of the entire house, and they are not perfect vacuums. Within these profound expanses drifts an incredibly diffuse gas, so thin it is almost a ghost, along with the mysterious presence of dark matter. Here and there, like solitary lighthouses in an endless ocean, a few isolated void galaxies might form, lonely outposts of star birth clinging to existence. This redefines our idea of nothing. It is not an absolute emptiness, but a specific state of the cosmos, a baseline condition against which all structure is defined. Understanding this void, this foundational emptiness, is the first step to unlocking everything that comes next. This vast emptiness is not just a feature of the cosmos, it is its defining characteristic. To truly grasp its scale, we need to shrink the universe down to a human size. Picture our entire Milky Way galaxy, a swirling disk of hundreds of billions of stars, reduced to the size of a dinner plate. In this scaled-down model, the distance from our galactic plate to the nearest edge of a great void would not be a few inches. It would stretch the length of an entire football field. That is the sheer, breathtaking emptiness we are talking about. A void so immense that entire galaxies are mere specks against its backdrop. One of the most famous examples is the Boötes void, discovered by astronomer Robert Kirshner and his team in the 1980s. This is a spherical region of space roughly 330 million light-years across. To put that in perspective, if you placed our Milky Way at one edge of this void, light would need to travel for 330 million years just to reach the other side. And what fills this colossal volume? When astronomers first pointed their telescopes toward it, they expected to see thousands of galaxies. They found only a handful, a few dozen lonely islands in an ocean of darkness. It was like looking at a map of a continent and finding a country-sized hole where nothing seemed to exist. Our understanding of these structures comes from monumental projects like the Sloan Digital Sky Survey, which has meticulously mapped the positions of millions of galaxies. These maps are not flat pictures, they are three-dimensional charts of cosmic geography. When you look at them, the story is undeniable. The bright knots and filaments of the cosmic web are there, but they are traced against a background of profound, sprawling darkness. The voids are not accidents or gaps, they are the dominant architecture. In fact, these empty regions make up over 80% of the total volume of the observable universe. This single statistic forces a dramatic shift in perspective. We do not live in a universe of stars, we live in a universe of emptiness, where stars and galaxies are the rare, glittering exceptions. This realization leads to a deeper, more pressing question. What immense force could possibly carve out these hollows, these bubbles of near nothingness that stretch for hundreds of millions of light years? The answer lies not in the emptiness itself, but in the faint, ancient echoes of everything. These voids are not just immense in space, they are ancient in time. How old is a void? Its story begins in the first fraction of a second after the Big Bang, within a sea of energy so dense and hot it defies comprehension. In that primordial fire, the universe was not perfectly smooth. Thanks to a process called cosmic inflation, a period of unimaginably rapid expansion, tiny quantum ripples were stretched to cosmic proportions. Think of blowing up a balloon with a faint, almost invisible pattern drawn on its surface. As the balloon inflates to a colossal size, that faint pattern becomes the defining feature of its entire landscape. Those stretched quantum ripples became the blueprint for all structure, the seeds of both the future galaxy clusters and the future voids. The slightly denser regions in that early plasma would, over eons, become the filaments and knots of the cosmic web. But the slightly less dense regions, the under-dense patches, were destined to become the great voids. This is the crucial shift in understanding. Emptiness is not an accident. It was written into the fabric of reality from the very first moments, an imprint of the universe's explosive birth. For billions of years, gravity acted as the universe's great sculptor. It pulled matter relentlessly toward those initial denser seeds, building up the walls and filaments of the cosmic web. But gravity works both ways. As it pulled matter into the bright structures, it simultaneously drained matter away from the under-dense regions. The voids did not just sit there, they actively evolved. They grew emptier and larger as the cosmos aged, their boundaries becoming more sharply defined as galaxies were pulled toward the gravitational pull of the surrounding web. We are witnessing a slow-motion expansion of nothingness. A void you observe today is not the same as it was 5 billion years ago. It is deeper, darker, and more pronounced. This adds a profound temporal dimension to the cosmic desert. When you look into a void, you are not just looking across space, you are looking back through a timeline of evacuation, watching the aftermath of a gravitational exodus that began nearly 14 billion years ago. This evolution of emptiness is not a side effect, it is a central character in the story of the universe's growth, and it begs a startling question. If gravity is constantly pulling matter out of the voids, making them emptier, what force could possibly be working in the opposite direction, stretching the voids themselves even wider on a scale that defies gravity's pull? The grandeur of a cathedral is defined not only by its soaring pillars but by the vast, open spaces between them. In the cosmic web, the voids serve this same architectural purpose. They are not passive blanks waiting to be filled, but active, defining components that give the universe its staggering three-dimensional structure. To understand this, we turn to the digital universes created by cosmologists, vast computer simulations like the famous Millennium simulation. These virtual cosmos begin with the faint ripples of the early universe and let the laws of physics play out over billions of simulated years. What they reveal is a beautiful and undeniable truth. The great voids are each surrounded by dense walls and filaments, like the empty chambers of a honeycomb outlined in wax. The distribution of luminous matter, the galaxies we see, is not random. It is sculpted and contoured by the presence of these immense hollows. The emptiness literally shapes the light. Leading cosmologists emphasize a profound point. Without these voids, the cosmic web would lose its definition. It would collapse into a homogeneous, featureless blur, like a painting where all the colors have run together. The emptiness provides the essential contrasting framework, the negative space that gives the positive structure its form and meaning. This is a complete reframing of our cosmic perspective. We are no longer looking for galaxies and ignoring the gaps between them. Instead, we are mapping the gaps themselves because their size, shape, and distribution tell us the most about the underlying skeleton of everything. Think of it like this: if you want to understand the shape of a mountain range, you do not just map the peaks. You chart the valleys, the passes, and the vast basins between them. It is the relationship between high ground and low ground that reveals the true topography. In the cosmos, the voids are those colossal basins, and by studying their architecture, we are essentially taking a survey of the universe's deepest gravitational geography. This shift is crucial for how we map the cosmos, turning our attention from the islands of light to the seas of darkness that give them their meaning. But if these voids are such fundamental architectural features, what does their ongoing evolution tell us about the forces that are not just shaping, but actively stretching the very fabric of the cosmos? Mapping an absence seems like a contradiction in terms. How do you chart a territory defined by what it lacks? For much of astronomy's history, the answer was a painstaking process of elimination. Astronomers would point their telescopes at a patch of sky and begin the meticulous work of galaxy counting. They would catalog every faint smudge of light, plotting their positions and distances. In most regions, the numbers would climb steadily, a celestial census revealing a bustling neighborhood. But sometimes the count would stall. A vast swath of sky would yield only a handful of galaxies where thousands were expected. This startling deficit, this great silence in the data, was the first clue to a void's presence. The discovery of the Boötes void unfolded exactly this way. It was not seen directly, it was inferred from a profound and unexpected scarcity. Today, our methods have transformed from simple counting to grand cosmic cartography. The key is the large-scale Redshift survey. When light from a distant galaxy travels across the expanding universe, its wavelengths stretch, shifting toward the red end of the spectrum. By measuring this redshift, astronomers can calculate not just how far away a galaxy is, but also how fast it is moving away from us. Projects like the Sloan Digital Sky Survey have used this technique to map the three-dimensional positions of millions of galaxies. The result is not a flat picture, but a point cloud of the cosmos, a digital universe we can explore. Within this immense dataset, voids are no longer just empty spots on a two-dimensional plate. They become palpable hollows in three-dimensional space. Astronomers can now identify a void by tracing its boundaries, the precise points where the dense wall of the cosmic web gives way to a precipitous drop in galaxy density. It is like mapping a canyon by charting the cliff edges that surround it. To make sense of these complex shapes, scientists employ sophisticated algorithms. These computer programs analyze the galaxy distribution and define the voids mathematically. They calculate each void's effective center, its volume, and its shape, whether it is roughly spherical or more like an elongated bubble. This process turns an intuitive concept of nothing into a rigorous, quantifiable entity. We are not just saying a region is empty, we are measuring the geometry of that emptiness with precision. This mapping of nothing is a profound testament to scientific ingenuity. It takes the fundamental challenge of observing an absence and transforms it into one of cosmology's most powerful tools. These precise maps of the voids are not an end in themselves, however. They are the foundation for the next great leap, because the structure of these empty regions holds encoded messages about the most mysterious forces in the universe. The shape and growth of nothing may be our best window into understanding everything. Deep within the vast cosmic desert, a single point of light holds its ground. This is a void galaxy, an island universe adrift in an ocean of darkness so immense it defies human comprehension. Picture our own Milky Way, but remove every neighboring galaxy from view. Erase the Magellanic Clouds, blur Andromeda into the distance, and extinguish the light from every other member of our local group. Now place this solitary galaxy in the heart of a void, where the nearest comparable island of stars is not 2.5 million light-years away, but tens of millions. You are left with a scene of profound isolation, a lone ship sailing on the darkest sea imaginable. Astronomers have given one of these objects a poignant nickname, MCG +01020015, known informally as the Loneliest Galaxy. From its vantage point, the entire observable universe would appear nearly empty, a handful of faint smudges pressed against the void's distant walls. Yet these lonely outposts are far from cosmic errors. They are exceptional natural laboratories. While galaxies in the dense clusters and filaments of the cosmic web live a life of constant interaction, gravitational harassment, and dramatic mergers, a void galaxy exists in a state of deep cosmic quiet. This isolation has profound consequences for its life story. Shielded from the violent gravitational tides that reshape cluster galaxies, void galaxies often experience a slower, more steady pace of star formation. They are not stirred up by close encounters, allowing them to hold onto their reservoirs of primordial hydrogen gas for much longer. This means they can potentially host older stellar populations and evolve in a more undisturbed, pristine fashion. Studying a void galaxy is like studying a tree that grew alone in a vast meadow, its shape and growth rings telling a story untouched by the crowding competition of a dense forest. Astronomers peer at these isolated systems precisely because they represent galactic evolution in one of its purest forms. By comparing the quiet, steady life of a void galaxy with the turbulent, merger-driven history of a cluster galaxy, we learn which traits are innate and which are sculpted by environment. The void is not a sterile blank. It is a unique habitat, and the galaxies that call it home, though few and far between, carry a unique signature in their light, a story of solitude written across billions of years. Their very existence, clinging to star formation in the deepest emptiness, challenges our assumptions and reveals a stunning diversity in how galaxies live their lives. But if these lonely galaxies are the only visible matter in the void, what unseen presence might still linger there, holding the very fabric of this emptiness together? Yet even in these profound deserts, the void is not a perfect vacuum. It holds a ghostly tenant, a faint and elusive presence that has long eluded our sight. This is the warm-hot intergalactic medium, often called the WIM. Picture the aftermath of a great cosmic party, where the vibrant crowds of galaxies have long since departed, but the air still hangs thick with a faint, dissipating warmth. The WIM is that lingering atmosphere, a tenuous plasma of superheated gas that permeates the vast expanses between the cosmic web's filaments. It is staggeringly hot, reaching temperatures of millions of degrees, which causes it to glow not in visible light, but in high-energy X-rays. To our optical telescopes, this makes it nearly invisible, a hidden component of the cosmos we have only recently learned to detect. For decades, cosmologists faced a perplexing puzzle. When they tallied all the normal or baryonic matter created in the Big Bang, the stuff of stars, planets, and us, a significant portion was simply missing from our inventories of galaxies and clusters. The WIM is the solution. This diffuse, hot gas is now understood to be a major reservoir of that missing ordinary matter, a hidden ocean that fills the intergalactic voids. So how do you find a ghost? Astronomers use a technique as elegant as it is indirect. They turn their telescopes to the brilliant beacons known as quasars, the luminous cores of distant galaxies. As the intense light from a quasar travels across billions of light-years to reach us, it passes through the cosmic web, including these vast voids filled with the whim. When that light finally enters our telescopes, its spectrum, its fingerprint of colors, bears subtle scars. Specific wavelengths are absorbed, creating dark lines that correspond to the signatures of elements like oxygen and hydrogen in that superheated gas. It is as if the quasar's light is a probe, illuminating the invisible material in its path. Each absorption line is a direct detection, a whisper from the whim itself, confirming its presence and allowing scientists to map its distribution and density. This discovery fundamentally transforms our understanding of the void. It is no longer a true nothing, but a repository, a hidden vault holding a substantial fraction of the universe's normal matter. The great emptiness is, in fact, subtly filled, solving a key piece of the cosmic missing matter puzzle and reminding us that even in the deepest darkness, the universe rarely leaves a space completely blank. But if this tenuous gas is the only ordinary matter we can now account for, what other, far more mysterious presence must also dwell within these voids to explain their immense gravitational architecture? Yet this tenuous hot gas cannot be the full story of the void's structure. If we account for all the normal matter, from galaxies to the whim, the gravitational math still does not add up. So we must ask a deeper question. What unseen presence, even more ghostly than hot gas, provides the true architectural support for these immense regions of emptiness? The answer lies with the universe's greatest mystery, dark matter. Cosmological simulations present a clear, if mind-bending, picture. While the great voids are profoundly empty of stars and glowing gas, they are not empty of dark matter. Instead, this mysterious substance forms a vast, smooth, and incredibly diffuse scaffolding that permeates the entire volume. Think of it as the faintest possible three-dimensional grid, an invisible framework upon which the entire cosmic web, including its empty chambers, is stretched. Its density here is far lower than in the brilliant filaments and dense clusters, but its presence is still fundamental. This leads to a crucial distinction. In the crowded nodes of the cosmic web, dark matter clumps into massive, dense halos that anchor entire galaxies. But in the voids, its distribution is far more serene and uniform. It is like the difference between the dense, gnarled roots of an ancient tree and the thin, widespread network of fungal filaments in the soil beneath a meadow. Both are structures, but one is concentrated and powerful, while the other is subtle and all-pervasive. This smooth, dark matter scaffold has a gravitational influence that is gentle yet inescapable. It subtly guides the motions of the few lonely void galaxies, their paths tracing the soft gravitational contours of the emptiness around them. More importantly, this dark matter framework dictates the very shape and growth of the void itself. When cosmologists run their universe simulations, they find that the precise way dark matter fills these under-dense regions directly affects how quickly the voids expand and what geometrical forms they take. Are they perfectly spherical or more like stretched, elongated bubbles? The answer depends on the properties of the invisible scaffold within. This makes the great intergalactic voids something far more significant than just empty space. They have become active cosmic laboratories. By meticulously measuring the shapes of voids and the motions of galaxies along their edges, astronomers can perform a critical test. They can compare the real universe against the predictions of different theories of dark matter and even alternative models of gravity itself. Does the dark matter in voids behave exactly as our standard models predict, or does its subtle influence reveal a crack in our foundational understanding? The great nothing, therefore, is not passive. It is an arena where the most fundamental forces of the cosmos are quietly at work, and by learning to read its invisible architecture, we edge closer to deciphering the true nature of reality. This profound emptiness does more than just hold secrets. It actively bends the fabric of perception. It might seem paradoxical, but the great voids can function as cosmic magnifying glasses. To understand this, we must first grasp the principle of gravitational lensing. According to Einstein's theory of general relativity, mass warps the space around it. A massive object like a galaxy cluster acts like a lens in spacetime, bending the paths of light rays from even more distant objects behind it. This creates spectacular effects, like multiple stretched images of a single background galaxy. Now here is the counterintuitive twist. An under-dense void, a region with less matter than the cosmic average, also warps space, but in the opposite manner. Think of a lens in a pair of glasses. A dense galaxy cluster is like a convex magnifying lens that bends light inward to a focus. A vast cosmic void, however, behaves like a concave or diverging lens. It gently pushes light rays outward as they pass through its immense volume. This creates a subtle but measurable signature on the oldest light in the universe, the cosmic microwave background. This relic radiation from the Big Bang fills the entire sky like a faint, cold glow. As this ancient light travels for billions of years to reach us, it passes through the evolving cosmic web. When a light wave enters a void, it must climb out of a gravitational well that is shallower than the surrounding regions. This process imparts a tiny amount of energy to the photon, very slightly shifting its temperature. This collective effect is known as the integrated Sachs-Wolfe effect. It is an incredibly faint imprint, a whisper of a temperature change measured in millionths of a degree, but it is there. By meticulously mapping these subtle distortions in the cosmic microwave background and cross-referencing them with the locations of known voids, cosmologists achieve something remarkable. They use the absence of matter as a precision tool. The strength and pattern of this lensing effect tell us directly about the geometry of the universe and the properties of dark energy, the mysterious force accelerating cosmic expansion. A void, therefore, is transformed from a passive emptiness into an active cosmological instrument. By studying how nothing bends light, we gain direct evidence for the forces that are stretching everything. The universe is not just expanding, it is accelerating. This discovery, which earned a Nobel Prize, remains one of the most profound puzzles in all of science. We call the mysterious cause dark energy, a placeholder name for a force that seems to be woven into the fabric of space itself, pushing galaxies apart faster and faster as time goes on. But what if the key to this acceleration is not found in some exotic new energy, but in the relentless growth of nothing? This is where the great voids enter the story as active, dynamic players. A compelling theoretical idea suggests that the expansion of these immense under-dense regions could, on the largest cosmic scales, create an effect that looks exactly like dark energy. Think of it this way: as gravity pulls matter out of a void and into the surrounding web, the void does not just sit there. It actively grows, its emptiness becoming more profound and its volume increasing. This is not a passive process, it is an aggressive evacuation. Now, imagine the collective effect of billions of these voids, each one expanding as the cosmic web tightens its grip on their borders. Some cosmologists propose that this large-scale flow of matter, this collective sigh of emptiness, could generate a kind of back pressure that drives an apparent acceleration of the universe's expansion. It would be a cosmic illusion born from structure, a ghost in the machine of gravity itself. This idea challenges the standard model of cosmology, known as the lambda-CDM model, which treats dark energy as a constant property of space. But the story grows even more intriguing when we consider our own place in the cosmos. Could our measurements of universal expansion be skewed because we live inside a local void? Some theorists explore this provocative possibility. If our Milky Way galaxy resides in a region of space that is slightly less dense than the cosmic average, a modest local void, then the gravitational landscape around us would be unusual. The pull from surrounding denser regions could subtly affect how we perceive the recession of distant galaxies, potentially altering our calculations of the Hubble constant, the rate of expansion. This is not a fringe idea, but a serious consideration that highlights how the architecture of emptiness directly influences our most fundamental observations. Insights from leading theorists now point to a powerful new test. By carefully measuring how the sizes of voids have changed over billions of years, by essentially taking a cosmic census of emptiness across different epochs, we can place independent constraints on the nature of dark energy. Does it behave as a true cosmological constant, or does its strength vary over time? The growth history of voids could hold the answer. This transforms our perspective completely. The great intergalactic voids are no longer mere backdrops or empty stages. They have become central characters in the drama of cosmic fate, their silent expansion potentially entwined with the very energy that will determine the destiny of all things. The profound emptiness of a void is more than just space. It is a kind of cosmic archaeology. These vast hollows are time capsules, preserving a direct imprint from the universe's explosive infancy. To understand how, we must return to those first unimaginable moments after the Big Bang, when the entire cosmos was a seething, nearly uniform sea of energy. The only variations were the faintest of ripples, quantum whispers in the fabric of reality. The theory of cosmic inflation tells us that in a fraction of a second, the universe expanded faster than the speed of light, stretching those quantum whispers to cosmic proportions. Those stretched ripples became the blueprint for all future structure, the seeds for both the dense clusters of galaxies and the immense underdense voids. This is the crucial link. The statistical properties of the voids we see today, their sizes, their shapes, and how they are distributed across the sky, are not random. They are a direct reflection of that original spectrum of primordial density fluctuations. Think of it like finding a collection of fossilized footprints. By measuring the depth, the spacing, and the direction of each print, you can reconstruct the size, the gait, and even the weight of the creature that made them. In cosmology, the voids are the footprints. A particularly large void, spanning hundreds of millions of light years, corresponds to an exceptionally large underdensity in that primordial blueprint. Its shape, whether spherical or elongated, tells us about the character of those initial ripples. This makes the great nothingness a fossil record, a preserved snapshot of the universe's quantum origins. We are using the largest structures in existence to probe physics at the smallest scales imaginable. This is why upcoming missions like the European Space Agency's Euclid telescope are so revolutionary. Euclid is designed to map the geometry of the dark universe with unprecedented precision, charting billions of galaxies and, by extension, the voids between them. By providing an exquisitely detailed census of void characteristics across cosmic time, these surveys will perform a rigorous test of our inflation models. They could tell us about the energy scale at which inflation occurred, a realm far beyond the reach of any particle accelerator on Earth. In this way, the silent, empty voids become our most powerful telescopes, not looking out across space, but looking back to the first fleeting instants of time. The Great Nothing is a window into the moment of creation itself, a profound and elegant link between the vast emptiness we see and the quantum spark from which everything emerged. Our journey through the cosmic web is not a gentle drift, but a turbulent river ride. For decades, astronomers have known our local group of galaxies, including the Milky Way, is not simply coasting with the universe's expansion. We are hurtling through space at a staggering 600 kilometers per second toward a mysterious region of the constellation Centaurus. This colossal gravitational anomaly is known as the Great Attractor, a massive concentration of mass hidden behind the dust of our own galaxy's plane, pulling entire clusters of galaxies toward its unseen heart. But gravity is a dance of push and pull. and a compelling new chapter in this story suggests an equal partner in this motion may not be a pull at all, but a great and powerful push from behind. This is the cosmic tug-of-war between the great attractor and the dipole repeller. The term repeller is a bit misleading, as nothing in gravity actively repels. Instead, think of it as a profound emptiness so vast that its lack of gravitational pull creates a relative push. Picture yourself in a swimming pool, holding onto the edge. If you let go, you do not move because the water actively pushes you away. You move because the solid edge offers a stronger pull than the water around you. In the cosmic ocean, the dipole repeller is hypothesized to be a gigantic void, an under-dense region hundreds of millions of light-years across, located in the opposite direction from the great attractor. Its profound lack of mass means it exerts a much weaker gravitational pull on our galactic neighborhood than the cosmic average. In the grand gravitational balance sheet, this deficit registers as an effective push. We are not so much being pulled toward the attractor as we are being pushed away from the repeller. The discovery of this dynamic is a masterclass in cosmic detective work. Researchers did not point a telescope and see a giant hole. Instead, they meticulously mapped the peculiar velocities of thousands of galaxies, their motions that deviate from the smooth flow of cosmic expansion. By analyzing these drifting paths, much like tracking leaves caught in a complex wind, they could work backward to infer the landscape creating the flow. The pattern was clear. The galaxies were streaming not just toward a point of great mass, but away from a point of great absence. This turned the map of our local universe into a relief of extreme contrasts, a valley of shadow opposite a mountain of light with us caught in the current between them. It illustrates a profound principle on the largest scales. The architecture of emptiness is just as influential as the architecture of matter. Our motion is dictated not by one hidden giant, but by the gravitational tension between a colossal something and a colossal nothing. This silent, invisible void may be shoving us through the cosmos as forcefully as any attractor pulls, reminding us that in the grand tapestry, the dark threads define the pattern as much as the bright ones. The universe cannot be recreated in a laboratory, but it can be built inside a machine. To understand the evolution of voids that span hundreds of millions of light years, we turn to the world's most powerful supercomputers, running monumental simulations that would take a single desktop computer thousands of years to complete. These are cosmological n-body simulations, and they begin with a virtual canvas of staggering scale, representing a cubic volume of space billions of light years on a side. Within this digital cosmos, programmers place not stars or galaxies, but tens of billions of individual particles, each one representing a massive clump of dark matter. This is the starting point, a model of the smooth, early universe seeded with the faint ripples we detect in the cosmic microwave background. Then, with a press of a button, the simulation begins. For weeks, the supercomputer's processors hum, calculating the gravitational pull between every single one of those billions of particles as time, in this virtual realm, speeds forward across 13.8 billion years. What unfolds is a breathtaking digital time lapse of cosmic history. You can watch as gravity's invisible hand begins its work, pulling particles toward the slightly denser regions. Filaments and knots of dark matter emerge, weaving the familiar cosmic web. And just as importantly, vast spherical hollows begin to form and grow between those filaments, the great voids. Their emergence is not programmed in. It is a natural consequence of the physics, a validation that our understanding of gravity and structure formation is fundamentally correct. These virtual universes are more than just pretty animations. They are indispensable laboratories. Scientists can run what-if scenarios, altering the initial conditions or tweaking the laws of gravity to see how the voids respond. Would they form faster or slower? Would their shapes be different? By comparing these digital experiments to our real-world maps of emptiness, we can refine our cosmological models with incredible precision. The simulation is a bridge between theory and observation, a proof that the great nothing we see is exactly what the physics of our universe demands. The silent cartography of emptiness is about to enter a new era of breathtaking clarity. For the first time in human history, we are building telescopes not just to see the light, but to map the darkness with a precision that was once pure science fiction. The next generation of observatories will act as cosmic void hunters, their digital eyes scanning the heavens to reveal the architecture of nothing in unprecedented detail. Leading this charge is the Vera C. Rubin Observatory, currently under construction in Chile. Its cornerstone project, the Legacy Survey of Space and Time, is a mission of staggering scale. For 10 years, its massive mirror and camera will scan the entire southern sky, not once, but over and over, creating the deepest, widest astronomical movie ever made. This relentless gaze will catalog tens of billions of galaxies, pushing our cosmic maps to fainter and more distant frontiers than ever before. With this deluge of data, the subtle boundaries of voids will snap into sharp focus. We will no longer see just the largest voids like Boötes, but millions of smaller under dense regions, a complete hierarchy of cosmic bubbles from the colossal down to the merely enormous. This statistical power transforms voids from interesting curiosities into a rigorous new science. We will be able to classify them by size and shape, study how they cluster together, and trace their evolution through cosmic time with a sample so vast it eliminates chance and reveals underlying laws. Joining this effort in space will be two revolutionary missions. The European Space Agency's Euclid spacecraft is already on its journey, designed specifically to probe the dark universe. It will measure the shapes and redshifts of over 1 billion galaxies, constructing a three-dimensional map of the cosmic web so detailed that the shapes of individual voids can be measured with geometric precision. Are they perfect spheres or slightly squashed? That subtle distortion holds clues to dark energy's push. Meanwhile, NASA and Nancy Grace Roman Space Telescope will combine a Hubble-like sharpness with a field of view 100 times larger. Roman will perform deep galactic surveys at infrared wavelengths, peering through the dust that obscures our view of the Milky Way's plane. This is crucial because it may finally reveal the full structure of our local cosmic neighborhood, including the true extent of the Dipole repeller, that proposed great void that might be pushing us through space. These observatories together create a perfect synergy. Rubin provides the immense panoramic census. Roman offers sharp, penetrating depth in key areas. And Euclid delivers exquisitely precise geometry and distance measurements. The combined data will be a treasure trove for void cosmologists. This incoming flood of information will turn voids into some of our most sensitive cosmological instruments. By tracking how the population of voids changes across different epochs of the universe, scientists can chart the expansion history of space itself with a new, independent method. The growth of nothing becomes a direct measure of the forces shaping everything. Furthermore, those isolated void galaxies, the loneliest islands in the cosmos, will finally be found in significant numbers. Studying a population of these pristine, undisturbed galaxies will tell us what a galaxy looks like when it evolves in perfect cosmic quiet, free from the bullying influences of crowded clusters. The next decade promises to fill our maps of the great nothing with richer information than we have ever possessed, transforming empty space from a passive backdrop into an active, data-filled field of discovery. Yet this immense power of observation leads to a final, humbling thought about the ultimate fate of all we see. The universe's preference for emptiness is a scientific fact with a deeply philosophical echo. After mapping the geometry of voids and the physics of their growth, we are left facing a quieter, more personal question. What does it mean that most of reality is not just unknown, but fundamentally uninhabitable, a form of structured nothing? The data compels a shift in perspective, one that has resonated with thinkers for centuries. The astronomer Carl Sagan, in his Reflections, noted that we are a way for the cosmos to know itself. Yet this self-knowing occurs in the tiniest, brightest corners of a realm dominated by darkness. Our human tendency is to focus on the points of light, the stars, the galaxies, the places where something happens. But the cosmos itself is overwhelmingly a place where nothing happens, at least nothing we would recognize as event or life. This realization instills a form of cosmic humility. We are not the center of the universe in location, and now we see we are not the center in substance either. Our reality is the exception, not the rule. This reframes our search for life and intelligence in a profound way. We often ask if we are alone, scanning the galactic dots for signals. But the architecture of the cosmos suggests a more foundational truth. Perhaps most of reality is simply not built for such things. Life may be an incredibly rare and fragile pattern that can only emerge under the most specific, sheltered conditions, on the dense walls of the cosmic web, far from the expanding emptiness of the great voids. Is this vast nothingness a necessary canvas the artist cannot create without an empty space to fill? In that sense, the void is the foundational stage, the silent background that gives the glittering performance of galaxies its meaning and allows the story of stars and planets to unfold. Without this immense emptiness, gravity would have pulled everything together long ago into a single, hot, featureless mass. The void is what gives the universe room to breathe, evolve, and create complexity. Yet it is also a reminder of our profound isolation. We are on an island of matter in an ocean of near nothing, and that ocean is growing. The great voids are expanding, and the cosmic web is stretching, meaning the islands of light are becoming ever more distant from one another. This leads to a poignant duality in our understanding. The same emptiness that made our existence possible also underscores its incredible improbability and its eventual solitude. The philosopher Blaise Pascal once wrote of the eternal silence of these infinite spaces filling him with dread. Today, we might temper that dread with awe. The dread comes from recognizing our scale and our fragility. The awe comes from the realization that we are here at all, conscious beings able to measure the void and ponder its meaning. This scientific journey through the great intergalactic void, therefore, does not end with a simple answer. It ends with a deeper appreciation for the question itself. By mapping the nothing, we have not diminished the something of our existence. We have framed it within its true, majestic, and humbling context. The stories we tell about the void reveal as much about ourselves as they do about the cosmos. Long before astronomers mapped the Boötes void, human imagination had already populated the darkness with profound fears and philosophical trials. In literature and film, the vast emptiness between stars is rarely just empty space. It is a character in its own right, often representing the ultimate unknown. Consider the haunting great nothing in the never-ending story, a force of literal oblivion that consumes the world of fantasia, representing despair and the loss of imagination. It is a powerful metaphor portraying emptiness not as passive, but as an active, devouring force that must be confronted and named to be defeated. This mirrors a deep-seated human anxiety, the fear that beyond the edges of our maps and understanding, there lies not just mystery, but an annihilating nothingness. Science fiction amplifies this theme on an interstellar scale. Countless episodes of Star Trek feature the crew of the Enterprise confronting trackless voids or negative space wedges, regions where navigation fails and the ship seems utterly alone. These storylines are less about alien encounters and more about existential challenge, the psychological strain of confronting infinite, featureless expanse. The void becomes a trial, a place where technology is useless and characters must face fundamental questions of purpose and identity. These narratives tap into a primal discomfort, the same unease that philosopher Blaise Pascal expressed centuries ago. Our stories transform the scientific concept of an under-dense region into a stage for human drama, where emptiness forces a reckoning. This cultural lens highlights a fascinating contrast. In our myths and movies, the void is almost always a barrier, a terrifying blank to be crossed or a destructive force to be escaped. It is the abyss that stares back. Yet the scientific reality, as we have explored, is fundamentally different. The great intergalactic voids are not barriers, they are the foundational architecture of the cosmos. They are not destructive forces but necessary components in a structured, evolving universe. They are integral, sculpting the web of galaxies and holding clues to dark energy and inflation. Science reveals a void that is dynamic and full of information, not a metaphorical wasteland. This divergence is where the bridge between myth and measurement becomes most illuminating. Our fictional portrayals of terrifying, existential voids are not wrong, they are emotionally true. They capture the profound human response to the scale and silence that science quantifies. Our ancestors looked at the dark spaces between stars and saw chaos or monsters. We look at the same darkness and see the warm, hot intergalactic medium and dark matter scaffolding. The fear in the stories and the data in the telescopes are two different languages describing the same overwhelming reality. One speaks to the heart, the other to the mind. Together, they show a species striving to comprehend its place in a universe where we are the rare exception, clinging to islands of light in a sea of profound, structured nothing. This cultural reflection ultimately brings us back to a humbling unity. The great void, whether in story or science, remains the ultimate mirror, reflecting back whatever we project upon it, be it our deepest fears or our most ambitious quests for understanding. The ancient Greeks named it chaos, the gaping, formless abyss that existed before the world. In Norse mythology, it was Ginnungagap, the yawning void where fire and ice first met to spark creation. Across cultures and millennia, human origin stories share a profound common thread. They almost always begin with an emptiness, a fertile nothingness from which everything else emerges. This is not a coincidence of mythology. It is a deep intuition about the nature of reality, an intuition that modern cosmology has now mapped with mathematics and light. Long before we had telescopes, the human mind was already wrestling with the concept of the void, recognizing it as both the precursor and the necessary stage for existence. The philosophical and spiritual traditions of the world are rich with this contemplation. In Eastern thought, the concept of sunyata, often translated as emptiness or voidness, points to the fundamental nature of reality as being empty of independent, permanent existence. It is a profound philosophical stance that sees interconnectedness arising from an underlying ground of potential. Similarly, the mystical traditions within Christianity, Judaism, and Islam explore ideas of kenosis, a voluntary emptying of self to make room for the divine, or of meditative states that seek unity with a vast, silent presence. These are not scientific theories, of course, but they are different modes of inquiry into the same profound mystery. What does it mean to confront the ground of being, the backdrop against which all things appear? They represent the timeless human effort to find meaning in the face of the immense and the unknown. Today, we are continuing that very same pursuit, but with new and powerful tools. Where myth spoke of chaos, our satellites map the cosmic microwave background. Where sages contemplated sunyata, our supercomputers simulate the gravitational collapse of dark matter. The great intergalactic void is our Ginnungagap, no longer a metaphorical abyss but a measurable, evolving feature of the physical universe. This historical context does not validate the myths with science, nor does it reduce science to myth. Instead, it enriches our understanding by revealing a continuous thread of human curiosity. We have always looked into the darkness and asked what lies within it and beyond it. Our ancestors populated that darkness with gods and monsters, with creative forces and destructive ones. We now populate it with diffuse plasma, dark matter scaffolds, and the imprints of quantum fluctuations. The question, however, remains strikingly similar. What is the nature of the nothing from which we came? This long conversation across centuries reminds us that the interrogation of emptiness is one of the most fundamental human endeavors, a quest that has moved from the realm of story and meditation into the precise, awe-inspiring domain of astrophysics. Blackness is not the absence of color, but a field of infinite depth. This is the aesthetic truth artists have long understood, and it is a truth that finds its ultimate expression in the contemplation of the cosmic void. Long before our telescopes could measure the density of the Boötes void, painters and sculptors were already grappling with how to represent the profound, how to make the emptiness felt. They approached the void not as a scientific fact, but as an experience, a sensation to be evoked on canvas or within a room. The American painter Ad Reinhardt, in his later work, created what he called the ultimate paintings, vast, nearly uniform black squares. At first glance, they appear simply black, but as you look longer, subtle geometric divisions emerge from the darkness. The painting does not show you emptiness. It becomes a portal into it, demanding a slow, meditative gaze that reveals complexity within what seemed like nothing. This is an artistic parallel to the astronomer's patient observation, where staring into a seemingly blank patch of sky gradually reveals the subtle architecture of the cosmic web. Reinhardt's black paintings are not depictions of space. They are experiences of it, using extreme minimalism to push the viewer to the edge of perception. This challenge of scale and suggestion is central to the artistic encounter with the void. How do you represent something that is defined by its lack of features, by distances so vast they numb the mind? Many artists answer by creating immersive environments that make you feel the emptiness bodily. James Turrell builds rooms filled with light that seems to have no source, crafting illusions of boundless space. Standing in one of his installations, the boundaries of the room dissolve, and you are left floating in a luminous, color-saturated void. It is a sensory translation of the cosmic experience, replacing the cold dark of space with a radiant, enveloping absence that is equally awe-inspiring. These works do not illustrate the science, they translate its emotional and perceptual impact. They use the tools of art, light, color, scale, and negative space to evoke the feelings of awe, solitude, and sublime vastness that the scientific data describes. This artistic drive highlights a profound intersection. Both the scientist and the artist are confronting the ineffable, that which is difficult or impossible to put into words. The scientist uses mathematics and measurement to map the void's physical properties. The artist uses pigment and perception to map its emotional and philosophical resonance. They are two different languages for the same profound inquiry. The minimalist composer John Cage created a piece titled 4 minutes 33 seconds, where the performer sits in silence and the music becomes the ambient sounds of the audience and the hall. This is a void in sound, a structured emptiness that frames the random, unnoticed symphony of the everyday world. It mirrors how the cosmic void frames the galaxies, making us aware of the background against which all structure occurs. This shared human endeavor to express the void reveals that our comprehension is not purely intellectual. It is also visceral and emotional. The aesthetics of emptiness add a necessary dimension to our exploration, reminding us that the cold equations of cosmology point toward a reality that can also stir wonder, unease, and a deep sense of beauty. The great intergalactic void, therefore, exists not only as a region of space or a philosophical concept, but as a cultural touchstone, a canvas upon which we project our deepest questions about scale, existence, and what it means to perceive at the very limit of understanding. The challenge of teaching the cosmic void is a lesson in perspective itself. How do you make a student feel the scale of an emptiness so vast it defies every earthly comparison? Educators and science communicators have met this challenge with remarkable creativity, building bridges of understanding from the abstract data to the human senses. The most powerful tools are now digital, transforming the immense catalogs from projects like the Sloan Digital Sky Survey into navigable universes. Imagine putting on a virtual reality headset and not just seeing a flat image of the cosmic web, but flying through it. You can soar down a filament of galaxies, a glowing highway of star cities, and then plunge into the adjacent void, watching the density of points around you plummet into a profound and spacious darkness. This is not passive learning, it is an experiential journey. You physically feel the transition from the crowded web to the empty expanse, gaining an intuitive, bodily understanding of the universe's true architecture. In planetariums and science museums, this experience is scaled up to a collective awe. Immersive Dome shows rapt audiences in visualizations that map the cosmic web not just in light but in sound. Data sonification techniques translate the density of galaxies into shifting tones and harmonies, so a dense cluster resonates with a rich, complex chord, while a void expands into a deep, sparse, and haunting silence. You are not just told about the structure, you hear its shape, feeling the emptiness as a distinct and measurable quality in the audio landscape. For a hands-on classroom demonstration, simple analogies make the concept tangible. A natural sea sponge becomes a perfect model. The solid material of the sponge represents the filaments and walls of the cosmic web, while the air-filled holes and channels are the void. Students can see and touch how the empty spaces define the structure just as much as the solid parts. A more dramatic demonstration uses a block of packing foam, carefully slicing it to reveal the interconnected bubbles within, a direct analogy to the vast, bubble-like voids in the three-dimensional lattice of our universe. These tools do more than convey facts, they build a framework for wonder. They take the counterintuitive idea that nothing is a dominant feature of reality and make it accessible, even beautiful. This translation from complex data to personal experience is vital. It turns modern cosmology from a distant, mathematical abstraction into a story about our home, a narrative where everyone can grasp the grand and humbling architecture of all that exists. By making the void tangible, we empower a new generation to look up at the night sky and see not just pinpricks of light, but the deep, structured silence that holds them apart, fostering a deeper appreciation for the delicate and rare island of matter we call home. A perfect vacuum is a theoretical idea that does not exist in our universe. The great intergalactic voids come incredibly close, but they are not true emptiness. This is the first and most important misconception to clear away. These regions contain a trace amount of ordinary matter, that diffuse, superheated gas known as the warm-hot intergalactic medium. They are also filled with the smooth, pervasive scaffolding of dark matter. So while the density is up to 100 times lower than the cosmic average, it is not zero. The void is a specific, measurable state, not an absolute nothing, nor are these voids places of perfect darkness. If you could float in the heart of the Boötes void and look out, you would not see a wall of black. The entire sky would be faintly glowing with the ancient light of the cosmic microwave background, the afterglow of the Big Bang itself, bathing everything in a cold, uniform radiance. Added to that would be the extremely faint, high-energy X-ray glow from the tenuous WIM gas. Your eyes might perceive it as an inky black, but sensitive instruments reveal a space illuminated by the most fundamental light in existence. This leads to another correction, the idea that nothing can exist within a void. We have already met the lonely void galaxies, those isolated islands of star formation that manage to cling to existence in the deep desert. But even beyond those rare outposts, the void is far from inert. That dark matter scaffold is there, and its gentle gravitational pull influences the motion of everything that passes through. The void is not a dead zone. It is a distinct environment with its own physical conditions and subtle dynamics. Perhaps the most critical misunderstanding is viewing these structures as static holes, like permanent pockmarks in the cosmos. Nothing could be further from the truth. Voids are dynamically evolving regions. As gravity pulls matter into the surrounding cosmic web, the voids actively grow, becoming emptier and larger over billions of years. They are expanding, their boundaries sharpening with time. This is not a passive background feature. It is an ongoing process central to the evolution of the universe's large-scale structure. Finally, we must address a sensational but persistent idea: the fear that a great void is approaching Earth to swallow our galaxy. This stems from a confusion of scale. Our local galactic neighborhood does have under-dense and over-dense regions. We are moving toward the gravitational pull of the Great Attractor and away from the relative push of the Dipole Repeller. But these are features within the cosmic web, not the apocalyptic approach of a billion light-year-wide emptiness. The great voids are the overarching architecture, the bubbles in the foam. We are located on a filament of that foam, and while we move within the web's currents, we are not about to fall off the edge into a bottomless pit. The universe is structured, not chaotic, and our place within it is governed by the gentle, large-scale flow of gravity, not by a lurking cosmic vacuum cleaner. Clearing away these myths does more than correct facts, it refines our wonder. The true nature of the void is more fascinating than any fiction, a dynamic, structured, and subtly filled expanse that forms the foundational stage of the cosmos. With this accurate picture firmly in mind, we can now ask the most practical question of all: what do we actually gain from studying nothing? Silence has a sound all its own. If the vacuum of space could carry a vibration, what would a great intergalactic void sound like to our ears? This is not pure fantasy, but a doorway into a new way of experiencing the cosmos through a process called data sonification. Astronomers are now translating the silent maps of the universe into symphonies, turning light and position into pitch and rhythm. In these cosmic compositions, a dense cluster of galaxies might become a shimmering, complex chord of high notes, a bustling city of stars. A filament of the cosmic web could translate into a flowing, melodic line, and the void, that vast expanse of profound emptiness, would manifest as something else entirely, a deep, resonant, rumbling drone so low it vibrates in your bones, or perhaps a stretching stretch of near silence, punctuated only by the faintest, loneliest of tones representing a solitary void galaxy. Projects like the Sloan Digital Sky Survey have been sonified, allowing listeners to hear the large-scale structure of the universe unfold over time. You are not just seeing a static image, you are hearing the architecture grow, with the voids providing the foundational bass notes that hold the entire composition together. This auditory experience, while a metaphor, is deeply revealing. It engages a different part of our perception, making the pattern of something and nothing feel immediate and visceral. You can hear the scarcity, you can feel the empty spaces as distinct musical elements, not just as gaps. It underscores that the universe is not a random scatter of points, but a structured arrangement with a specific rhythm and texture, a rhythm dominated by the long, slow notes of emptiness. This sensory approach invites us to consider other metaphors, to wonder how we might feel the chill of the void or sense its gravitational contours if we had different senses. It reminds us that science is not just about numbers on a page, but about expanding human experience, finding new ways to connect our fragile, earthly perception to the grand and silent architecture of all that exists. Our maps of emptiness may be pointing toward an even deeper frontier. The great voids we have charted could be more than just features of our universe. They might be a cosmic clue, a pattern repeating on a scale so vast it redefines reality itself. This leads us into the realm of profound theoretical speculation, where cosmology meets the concept of the multiverse. Consider a startling thought experiment. We know our observable universe is filled with these immense, bubble-like voids. But what if our entire cosmos, with all its galaxies and its own cosmic web, is itself just a single, solitary bubble, floating within an inconceivably larger void of a meta-cosmic structure? In this dizzying perspective, the voids we study would be like tiny pores within the wall of our own cosmic bubble, microscopic analogues to the truly unimaginable expanses that could separate whole universes. This is not pure fantasy, but an extension of leading cosmological theories, particularly the idea of eternal inflation. This theory suggests that the rapid, exponential expansion of space that occurred during the Big Bang never truly stopped everywhere. Instead, it continues eternally in a background, hyperinflating space. Within this roiling, expanding medium, random quantum fluctuations can cause pockets of that inflation to slow down and crystallize into stable universes like our own, each with potentially different physical laws and constants. Our entire cosmos, in this view, is one bubble in a frothing, infinite sea of inflating space, with other bubble universes forever separated from us by stretches of hyper-expanding void that light can never cross. The voids within our universe, then, become a fascinating echo of this grander architecture. Studying their formation, their growth, and their ultimate fate provides a tangible, local laboratory for thinking about processes that might operate on a meta-cosmic scale. While we may never obtain direct evidence of other bubble universes, the physics that governs the structure and evolution of our own cosmic voids helps to constrain and inspire these mind-bending theories. It pushes cosmology to its philosophical limits, forcing us to ask what reality truly encompasses. Are we mapping the interior of a single, magnificent room, or are we tracing the patterns on a single tile in an infinite, unknowable cathedral? The great intergalactic void, therefore, becomes more than a subject of study. It becomes a lens, focusing our gaze from the largest structures we can see toward the ultimate horizons of existence itself. Given that emptiness defines most of reality, our own location seems like a remarkable accident. We are not drifting in a great void, but are nestled within a dense filament of the cosmic web, part of a bustling galactic neighborhood. This apparent luck, however, may be no accident at all, but a logical necessity of our own existence. This line of reasoning is known as the Anthropic Principle, specifically in its weak form. It simply states that the universe we observe must be compatible with the existence of conscious observers like us. We could not find ourselves looking out from a planet in the heart of a billion light-year void, because such a place could never have given rise to us in the first place. Consider the ingredients for life as we know it. They are not primordial. The hydrogen and helium born in the Big Bang are not enough. We require heavier elements, the carbon in our cells, the oxygen we breathe, the iron in our blood. These elements are forged in the nuclear furnaces of stars and scattered across space in spectacular supernova explosions. That process requires multiple generations of stars living and dying, a cycle of cosmic recycling that only occurs in regions dense enough with matter to form stars repeatedly. A deep void, with its profound scarcity of gas and its lack of galactic neighbors, is a cosmic desert incapable of such prolific stellar generations. It is a resource-poor environment, a place where the necessary ingredients for planets, let alone life, simply never accumulate. Therefore, our observation that we are not in a void is not a bizarre coincidence, it is a selection effect. Observers will only ever find themselves in locations where observation is possible. This principle provides a profound philosophical answer to our place in the cosmic web. We are not at the center of the universe, but we are necessarily in a special kind of place, one of the rare, glittering intersections where the conditions for complexity and consciousness have had time to emerge. It turns our location from a statistical puzzle into a fundamental feature of a universe that allows for understanding. To map the great nothing is essential, but to comprehend why we are here, looking out from a point of something, requires us to acknowledge that the cosmos must be structured in a way that allows for the observer. The profound emptiness we have mapped is not a wasteland, it is a frontier. As we look toward a future where humanity might one day journey between the stars, we must confront a new kind of question, not of physics, but of philosophy and ethics. How should we regard these vast intergalactic voids? They are more than just the empty highways between destinations. They are a unique and fundamental part of the cosmic environment. Perhaps we should begin to think of them as a cosmic commons, a shared heritage that belongs to no single civilization, but to the universe itself, a space held in common for all who might someday traverse it. This perspective shifts our relationship with the emptiness from one of mere utility to one of stewardship. Consider the potential future uses of these profound quiet spaces. Far from the brilliant glare of galactic cores and the radio chatter of dense star clusters, the deep voids would be the ultimate astronomical observatories. Placing telescopes in the heart of such emptiness would offer a view of the cosmos almost entirely free from light pollution, peering into the deepest secrets of the early universe with crystalline clarity. These regions could become preserves for pure science, sanctuaries of silence dedicated to listening to the faintest whispers of creation. On an even grander scale, these voids could serve a vital sociological function for a galaxy-spanning civilization. They are natural buffers, immense tracts of neutral territory that inherently separate different stellar communities. Just as oceans and mountain ranges have historically defined cultural and political boundaries on Earth, the great voids could provide necessary breathing room between potentially disparate galactic societies, reducing the potential for conflict simply by the sheer, peaceful distance they impose. This is, of course, highly speculative, a vision stretching thousands of millennia into the future. Yet the exercise itself is profoundly important. It encourages us to think about our long-term relationship with the cosmos not as conquerors but as participants. It asks us to extend a sense of respect and responsibility beyond the vibrant islands of matter to the silent seas that connect them, recognizing the void's role in the cosmic ecosystem as an architectural foundation, a preservative of primordial conditions, and a potential zone of peace, cultivates a stance of humility and care. It is a reminder that even the great nothing has value, and that as we reach out into the universe, our greatest legacy may be measured not by what we take, but by what we choose to leave undisturbed. We have traveled from seeing darkness as a simple absence of light to recognizing the great intergalactic void as a dynamic and structured reality. These immense regions are not blank spaces, but the dominant architecture of the cosmos, the foundational volume that shapes the universe's very form. They are not truly empty, but subtle laboratories where we test the nature of dark energy and map the invisible scaffold of dark matter. They are cosmic archives, preserving the faint imprint of quantum ripples from the first instance of the Big Bang. Most of all, they are the essential negative space, the silent canvas that gives the glittering filaments of the cosmic web their meaning and definition. This journey reframes our place in existence. It instills a profound humility, knowing we inhabit a rare and vibrant exception in a universe ruled by vast, structured emptiness. Yet it also celebrates the extraordinary reach of human curiosity, our ability to measure the immeasurable and find meaning in the void. So the next time you gaze at the night sky, remember this. The darkness between the stars is not a mere backdrop. It is a deep and dynamic part of our incredible universe, a story written in absence, waiting to be understood. What does this cosmic perspective make you feel? Share your thoughts in the comments below and subscribe to join us on our next voyage into space's greatest mysteries.